now that we have these two important trigonometric limits, and I'll restate the limits here in a second, we now have everything that we need to figure out what the derivative is of all six trigonometric functions, right? So all six functions, meaning sine, cosine, tangent, secant, cosecant, cotangent, we have all the tools to figure out the derivatives of those functions, and that's our next big goal, right? But just as a reminder, right, here are the limits that we previously derived. So we established that the limit as x approaches 0 of sine of x over x, that's equal to 1, right? Now, the use of the letter x here is not significant. I mean, let's say the limit was as t approaches 0 of the sine of t over t. It would still be 1. What's important is this ratio and the fact that the limit is with respect to whatever your variable is approaching 0, right? So again, it could be any letter there. So we prove that one using our squeeze theorem. And the second one that we proved using algebra and a couple trig identities is that the limit of cosine x minus 1 over x as x approaches 0, that's equal to 0, right? Now, let's say I multiplied this left-hand side by negative 1, and I multiplied the right-hand side by negative 1. Well, the right-hand side would still be 0, and then what I would have is this. So I could have a negative there, and then I would have the cosine of x minus 1 over x, right? And then if I distributed that negative sign, and the numerator, basically the terms in the numerator will get flipped. I would end up with a positive 1 and then a minus cosine x over x. That's equal to 0, right? So it turns out, and that's because this is equal to 0, that it doesn't matter if you have cosine x minus 1 or 1 minus cosine x, as long as you have it divided by x and your limit is as x approaches 0, then this result holds. And similarly here, the use of the letter x is not significant at all, right? So I could have the limit as p approaches 0 of 1 minus the cosine of p over p, well, that would still be 0, right? So I just wanted you to kind of see the different versions of this, and the letters aren't significant. The only thing that's significant is what the form of this fraction is, and the fact that your variable is approaching 0, all right? So now that we have those, let's start with the sine function. So let's start with sine of x, right? And we want to know what its derivative is. Well, when we don't know a derivative, we have to go back to the limit, right? So we have to go back to a limit, and then dy dx is going to be the limit as h approaches 0 of, and then I have to replace this x with x plus h. So it's the sine of x plus h minus the sine function all over h, right? So then what can we do, right? Well, again, we don't have like a polynomial, for instance, where we can just FOIL things out. This is a trigonometric function. It has completely different properties. In fact, one of those properties is something that's covered in trigonometry, and it has to do with the sum or difference formula for sine or cosine. In other words, there's an identity in trigonometry that will allow me to write this in terms of the sine of x, the sine of h, the cosine of x, and the cosine of h. So what I'm going to write down over here is called the sum identity or some formula for the sine function, right? And so I'll write it the way it normally is written in a trig class. They usually use like a and b, right? But they would say that the sine of a plus b is equal to the sine of a times the cosine of b plus the sine of b times the cosine of a, right? And what this formula, this identity from trig, right? In fact, that's I should probably use the word identity as opposed to formula, but in this context it means the same thing. I can express the sine of the sum of two things as this expression. Now, obviously, this expression looks more complicated, but this is exactly what we need in our limit definition of the derivative, because that's exactly what we have. We have the sine of x plus h, right? So now let's see what we can do by expressing this part, right, by using this identity. So a is going to be, or let me put it this way, x is going to be my a, and h is going to be big B, right? Okay, so let's write that down and see what happens. So we have the limit as h approaches 0. So basically, that identity allows me to expand this. So not like the binomial expansion, but this is more a trigonometric kind of expansion. So I'll end up with the sine of x times the cosine of h plus the sine of h times the cosine of x, right? So that's everything I have boxed off here. That's this using my identity, and then now minus the sine of x, and that's all over h. All right. Now, what can we do with this? Well, we can split this into two separate fractions. So this is what I'm going to do. So I'm going to say this is the limit as h approaches 0. Use some square brackets there. Now, I notice there are two terms in the numerator that have the sine of x. So I do see a common factor there. So I'm going to group those two terms and put them all over h. So let's do this. So the sine of x, I can factor that out, and then I'll have the cosine of h minus 1, like that. And then that's all over h. Right? So that takes care of these two. And then I still have this 1 in the middle. So then I'll write that as a separate fraction, and that will be the sine of h times the cosine of x all over h, right? And again, now looking at this, I see those two important trigonometric limits. I see this one, and I see this one. And I know that they both exist, right? And look, the other two, like the sine x here, doesn't involve an h. So for the most part, this is unaffected by the limit, right? Also, this is unaffected by the limit. So it allows me to do this. So the sine of x, that is unaffected by the limit because there's no h in this factor. So essentially what I can do is factor it out. And then I have what's left is the limit as h approaches 0 of the first thing I have in red. So that's the cosine of h minus 1 over h. And do the same thing. Again, this factor of cosine of x doesn't involve h, right? And so I can factor that out, and then I have the limit as h approaches 0, and then I have the sine of h over h. And these are the two that we proved. This limit is equal to 0, and this limit is equal to 1, right? And that's why they're important, because you're working through this limit definition and you get to this point, you're like, oh wait, I need to know what this is, and I need to know what this is. But we did that work previously. That was the whole reason of doing that work. So what we have now is the sine of x times 0 plus the cosine of x times 1. So that simplifies to the cosine of x. And that is the derivative of our sine function. So let's summarize that. So in summary, if y is equal to the sine of x, then dy dx is equal to cosine of x. Really remarkable result that when you differentiate the sine function, you get the cosine function, right? And it turns out there is a similar result, and the proof it's not identical, because it starts with the cosine function, and it needs the cosine identity, but these two limits also pop up, and when you apply these two results, you get this other formula. So now I'm going to write down. So this one, since the proof is very, very similar here, in fact, it would be a good exercise for you to go through it, kind of mimic the process that I just outlined for the sine function. But what you'd have to do is you'd have to find the sum identity for the cosine function and use it in a very similar way. But it turns out if your function is the cosine of x, then its derivative is the negative of the sine of x, right? And that's essentially what this video is going to entail. I will derive a result for one trig function and the one whose derivation or proof is very, very similar. I'll just state the result. Otherwise, this video would go on and on and on forever, right? And as much as we love calculus, forever is a long time. All right, so we have 2 out of the 6, right? So we now know that the derivative of the sine of x is the cosine of x, and the derivative of the cosine of x is the negative sine of x. All right. Now let's turn to the tangent function, right? What about tangent? Well, it turns out tangent has its own set of identities as well. They all do. All the trig functions, they have their own version of all the identities. But the thing is, we don't need a limit anymore, because once you know these two, every other trig function can be expressed in terms of sine and or cosine. So what we can do is instead now of using the limit, as much fun as limits are, right? We can then use the trigonometric definitions and see what other rules that we know that could apply, right? So let's start with the tangent function. So if y is equal to the tangent of x. In fact, when we were deriving one of those special trigonometric limits, we used the fact that tangent is equal to sine divided by cosine. So basically, tangent can be expressed as a quotient. And look at it. We now know how to differentiate the top. We now know how to differentiate the bottom. We have a quotient rule, right? That tells us how to put all these pieces together. So we should be able to use our quotient rule to derive the formula for the derivative of tangent. So using the quotient rule, instead of using our limit definition, right? So using the quotient rule, right, dy dx, right, so for tangent, let's see what we get. So the quotient rule says take the derivative of the top. Well, the derivative of sine, we just proved it, is cosine of x. And then I have to multiply by the bottom. So this is times cosine of x. And then it's minus the top, which is sine of x, times the derivative of the bottom. And the derivative of cosine is negative sine. Right? And then that's all over the bottom squared. So cosine squared of x. All right. Well, let's see. So multiplying these two gives me cosine squared x. Multiplying these two, now both of these factors have a negative sign in front of them. So multiplying gives me a positive sine squared. And at the bottom, we still have the cosine squared. Right? But look at the top. There's that fundamental trig identity again. That cosine squared x plus sine squared x, that's always equal to 1. So I have it as 1 over cosine squared x. But by definition, I know that, okay, so I can write it like this. So this is 1 over cosine of x times 1 over cosine of x, right? But by definition, the reciprocal of cosine is secant. So this is secant x times another secant x, and we get secant squared x. And that's how the derivative of tangent is normally expressed. There are other ways it can be expressed, right? But this is I would say, the more compact or the simplest form for the derivative of tangent. All right, so again, let's summarize. Right, so if y equals the tangent of x, its derivative is secant squared of x. All right, so let's see. We have sine, cosine, tangent, check. Now, it turns out for cotangent, right? For cotangent, the result is very, very similar. And if you notice, what I'm doing is I'm not deriving the result for the co-ratios, all the ones that start with a C. I'm doing the non-co-ratios, if you want to say it that way, and then just stating that the proof would be pretty much identical. You'd use the same, version of the identity. You just end up doing something slightly different. So now what I will state is the derivative of cotangent of x, right? And then we will have 4 of them completed. So if y is equal to the cotangent of x, then it turns out that that derivative, so dy dx, is negative cosecant squared x, right? And you're going to notice a pattern. All the trig functions that are co-ratios, like cosine has a derivative that's negative sine. Cotangent has a derivative that's negative cosecant squared. And we have our last pair, right? I won't spoil the result just yet, but what we have left is secant and cosecant. So in keeping with my pattern, I'll show you what the proof is for secant x, and then we can write down the result for cosecant, right? And then we have all 6 derivatives that we need, right, for these trigonometric functions. All right. So our last pair. So what about the secant function? What can we do with that? Well, we just used it above, that secant and cosine are reciprocals of each other. So what I can do, I can write secant as 1 over cosine. And again, since I can express it as a ratio, as a quotient, I can use the quotient rule, right? So, and this is a good one because we haven't really used the quotient rule where we have a constant in the numerator, but it still works. It's still a fraction. I can still differentiate the top. I now know how to differentiate cosine, and let's use our quotient rule to put it all together, right? So using the quotient rule, the derivative for this function, well, this is what it's going to say. It says take the derivative of the numerator. But when I differentiate my constant, I'll get 0, and then times the denominator, and then minus the numerator, which is 1, times the derivative of the denominator, and the derivative of cosine is negative sine, so we have that. And then it's all over the denominator squared, so cosine squared, right? And just as a reminder, and this just has to do with the notation. Whenever we write something like this, what's implied is that it's the cosine of x squared, right? If you don't write that x there, if you just write the cosine squared, that means nothing. This is just a string, cos, and then you somehow are going to square that, right? The cosine by itself doesn't mean anything. It has to be applied to something else, whether it's a variable or a number or another function in the case of a composite, right? But get into the habit. It's all, if you just write down cosine, well, cosine of what, right? It's like when you hit the cosine button on your calculator, if you don't hit anything else, it's not going to do anything. It's waiting for you to complete that statement, right? All right, so let's see how this simplifies. Well, the first term there is 0, right? And then we have a plus sine x because of these two negatives. So the numerator simplifies to sine x. And then what I'm going to do in the denominator is write this cosine squared as cosine x times cosine x. Very similar to what I did earlier, right? Now why am I doing that? Is because even though this is the derivative, it's not in its most simplified form. Right? So what I can do is I can write this fraction as the sine of x over cosine of x times 1 over cosine of x. And sine of x divided by cosine of x is the tangent of x. And 1 over cosine is secant x. And that's the derivative of secant x. It's the product, and we normally put the secant first, right? We normally say it's secant x times the tangent of x. Let's summarize that one and box it off. So in summary, if we have our secant function, so like that, then its derivative dy dx is secant x times tangent x, right? And it turns out that the derivative of cosecant is very similar. But here is the pattern again. It's going to be negative, and it's going to be negative cosecant times cotangent. So all the co-ratios are all together, and they all have this negative in front of their derivative. So here's our final one. So we've made it to 6. So if y is equal to cosecant of x, then its derivative is negative cosecant x cotangent x. All right? And there we have it. We now have the ability to differentiate all 6 trigonometric functions, right? Now, in the spirit of full disclosure, the most important ones that we will use will involve sine, cosine, and tangent, right? Every now and again you'll get a secant. Very rarely will you get a cosecant, except in those questions where they're just making sure that you have the ability to differentiate any of them. But the ones that show up in other applications, definitely cosine and sine are the top two. Tangent is a close third, and then secant, and then the rest, like cotangent and cosecant, you don't really see those a lot. But top four, tied for first, sine and cosine. Third is tangent, and then fourth is secant, right? And the good thing is, it's not about just memorizing these, but it's like using them as soon as we have an idea of the results. So let's do just one example. Let me just do one example of this to see how we can utilize these results. So let's say here's our function y equals e to the 3x times the cosine of x. And let's say we want to find the derivative of this, right? And this is what you'll start to see a lot. You'll start to see, as soon as you learn how to differentiate a new type of function, you'll see that function being combined with all the previous ones. So in this case, I have an exponential function, but it also involves a composite with a linear function, and then that is being multiplied by a trigonometric function. So let's see what the derivative would be. So let's identify everything that we're going to need. Because there's a product, right? These two functions are being multiplied. I have to use the product rule. And because of this composite, I have to use the chain rule. So the product rule says take the derivative of the first function. And that is going to give me e to the 3x times 3, right? In fact, this was one of those important results that I mentioned when we did the chain rule, is that you tend to use the exponential rule along with the chain rule a lot when you have something like e to a constant times your x, right? So that's the derivative of the first, and then times the second, and then plus the first, so we get back the e to the 3x. And then now we get to utilize our newest rules. The derivative of cosine is negative sine, so times negative sine of x, right? So let's look at different ways that this can be written. Certainly I can write the 3e to the 3x cosine x like that. Now, this coefficient is a positive 1. This coefficient is a negative 1. So the product is going to be a negative e to the 3x sine of x. And then another way that again, a lot of students like to write this, they realize that, hey, the e to the 3x is a common factor. So I could factor out the e to the 3x, and then that leaves me 3 cosine of x, and then minus sine of x in parentheses, right? So again, all of these are the same. It's just equivalent forms of the derivative of this function, all right? I hope you found that interesting, and see you in the next video.